Assalamu alaikum. Today on 2nd January 2021, I am starting lecture number 1 for week number 13, and the topic of my lecture is brushless exciter and pilot exciter. Earlier we have studied that in synchronous generators we need to provide a separate DC source for the provision of DC field current to the rotor's winding. Generally, in AC machines, field circuitry is located at the rotor of the machine, while the armature circuitry is located at the stator of the machine. Since the magnetic field of the rotor's winding is dominant, therefore it is known as the field winding. And since main voltage is induced or produced at the stator's winding, therefore stator's winding is known as the armature winding. Now, how can we provide DC field current to the rotor's winding in case of synchronous generators? There are three different ways to perform this task. Number one, the use of slip rings and carbon brushes that we have studied in the last lecture. Number two, uh, brushless exciter that is displayed in this figure. And number three, the pilot exciter. So what was the slip rings and carbon brushes scheme? In that scheme, we mount metallic slip rings on the rotor of the machine. We connect the first end of the rotor winding to the first slip ring and the second end of the rotor winding at the second slip ring. Now we connect the positive supply of a battery to the first carbon brush and the negative supply of the battery to the second carbon brush. These two carbon brushes continuously write on the slip rings. So when the rotor rotates, slip rings rotate, but carbon brushes remain stationary, but they remain riding on the slip rings, and hence they provide positive and negative DC supply to the rotor's winding by virtue of slip rings. But what was the disadvantage of this scheme? Due to this constant friction between the carbon brushes and the slip rings, carbon brushes get damaged because they consist of a soft material carbon while slip rings are metallic. So due to this constant friction, carbon brushes become uh, you know they become damaged. So what happens that periodically we need to replace the carbon brushes with the newer one, and to perform this duty we need to shut down the generator, then open it up, and then replace the carbon brushes, and then we can start it again. Now this is a disadvantage that cannot be afforded while the generator is a big synchronous generator that may be mounted on the dam, on a hydroelectric dam, or somewhere where we are producing electricity continuously. For example, uh, suppose in Kotandu power station where we need to produce electricity using the gas fuel. So obviously the generators mounted there are the synchronous generators, but they may run for hours and hours continuously. Now, if we need to replace the carbon brushes, this is not feasible. This is not viable for those generators. So to overcome this periodic replacement of carbon brushes, uh, machine designers offered two different solutions. The first solution is the brushless exciter that is basically displayed here. So what we do in a brushless exciter? In a brushless exciter, we do not use slip rings and carbon brushes. Instead, we provide DC field current to the synchronous generator by virtue of a smaller synchronous generator. So, what is the scheme? Coming to the figure, this rectangle shows the rotor of the bigger synchronous generator, while, while this rectangle shows the stator of the bigger synchronous generator. So we use a smaller synchronous generator to energize or to start the bigger synchronous generator. Okay, let me clear one thing before I start to explain this figure. A synchronous generator needs field current in addition to the mechanical energy to produce electrical energy. In chapter 1, we have studied that electric generators are those machines that convert mechanical energy into electrical energy. It is true, but in case of synchronous generator, there is one additional requirement, and that is the provision of DC field current. If its rotor winding is not provided the DC field current, in addition to the mechanical energy, it will not produce electrical voltage. It will not produce electricity. So the main requirement of a synchronous generator, whether it is a big synchronous generator or it is a smaller synchronous generator. So the basic requirement is to provide DC field current to its rotor winding and to provide mechanical energy to it so that it can produce electrical voltages. So here in this figure, this is the place where the bigger generator is basically provided the DC field current. Main field means field winding of the DC field current. Field winding of the bigger synchronous generator. So this is the place where we have provided field winding or DC current to the bigger synchronous generator. And when a bigger synchronous generator receives this field current, in addition to the mechanical energy to its shaft, what happens that it produces three-phase set of voltages at its terminals. So here, where I made a circle, the bigger synchronous generator has produced three-phase set of voltages. So this is electricity. These three-phase set of voltages are basically electricity. If we connect a three-phase load at this position, a current will flow through the load and the load will start working. So these are the two major places in this figure. The upper one is the place where we are providing DC field current to the bigger generator, while in the lower place the bigger generator is producing electricity, which is in actually our product. We are producing electricity by means of this synchronous generator. But the question is that how can we provide this DC field current to the bigger synchronous generator without the use of slip rings and carbon brushes? So the answer is that this DC field current is provided by these three-phase set of voltages. And these three-phase set of voltages are the output of the smaller synchronous generator. So the smaller synchronous generator produces three-phase set of voltages at its output, and this output is being transformed into a DC current by a three-phase rectifier. So this three-phase rectifier converts the output of the smaller AC generator into DC field current of the bigger synchronous generator. Now, how a smaller AC generator can work without slip rings and carbon brushes? So the answer is the smaller AC generator was fed using a low three-phase supply, a low current three-phase supply, because a smaller AC generator also needs DC field current. So here what we do, we provide DC field current to the smaller AC generator with the help of a three-phase supply. Obviously, this three-phase supply provides three-phase set of voltages. We used a three-phase rectifier to convert these three-phase set of voltages into DC field current of the smaller generator here, which is known as exciter field. And then the exciter, with the virtue of the mechanical energy provided to it and the DC field current provided to it, it produces three-phase set of voltages at its output, which is then rectified to provide DC field current to the bigger synchronous generator. So this is the entire scheme. If you closely analyze the figure, you can easily identify that in this scheme we have avoided slip rings and carbon brushes, but instead of a DC power supply, here we need a smaller AC power supply, which is written as three-phase input low current. So although this scheme is better as compared to the slip rings and carbon brushes, because there is no slip ring that is to be replaced after some time, but this scheme is not a totally independent scheme. Why? Because still we need a smaller AC supply to provide DC field current to the smaller AC generator, and if this three-phase AC supply is not there, then the bigger synchronous generator may not work, because if the smaller AC generator will not work, it will not produce three-phase set of voltages that will be rectified to provide DC field current to the bigger synchronous generator. So entire scheme will not work. So although this scheme is better than the slip rings and carbon brushes, it is expensive than the slip rings and carbon brushes scheme, but still it is not independent. So to make an independent scheme, electrical machine designers suggested the final version of provision of DC field current, which is known as the pilot exciter. This is the figure that will explain you that how a pilot exciter works to provide DC field current to a bigger synchronous generator. जी, तो यहाँ पर ये जो मैंने आपको बताया है, पहली स्कीम है ब्रशलेस एक्साइटर। तो इसमें कोई सवाल है, आप कोई कुछ पूछना चाहते हैं, कोई चीज आपको ऐसी जो समझ ना आई हो? जी, मैं इसको दोबारा से एक छोटा सा एक्सप्लेनेशन उर्दू में भी देता हूँ। वो ये कि देखिए, जब भी एक सिंक्रोनस जनरेटर हम यूज करना चाहते हैं ना इलेक्ट्रिसिटी प्रोड्यूस करने के लिए, तो याद रखें कि हमें उसे एक मैकेनिकल एनर्जी भी देनी है और उसको एक फील्ड करंट भी देनी है। अब ये सारा ब्रशलेस एक्साइटर या पायलट एक्साइटर का जो गेम है वो सिर्फ और सिर्फ फील्ड करंट के लिए है, क्योंकि मैकेनिकल एनर्जी तो जनरेटर की शाफ्ट को घुमाने से ही मिल जाती है उसे। अब चाहे वो घुमाएं हम टरबाइन से, या वो किसी मोटर से घुमाएं, या किसी भी और तरीके से घुमाएं, तो घुमाने से मैकेनिकल एनर्जी तो मिल जाती है, लेकिन फील्ड करंट नहीं मिलती। तो फील्ड करंट देने के लिए बड़े जनरेटर को यहाँ पर क्या स्कीम यूज की कि एक छोटा जनरेटर यूज कर लिया। छोटे जनरेटर को थ्री फेज सप्लाई दी और थ्री फेज सप्लाई को थ्री फेज रेक्टिफायर से गुजारा ताकि छोटे जनरेटर को फील्ड करंट, डीसी फील्ड करंट मिल जाए। रेक्टिफायर से गुजारते इसीलिए कि एसी को डीसी कन्वर्ट कर दें। तो फिर जब छोटे जनरेटर को डीसी फील्ड करंट मिला, उसने अपनी आउटपुट पर बड़े पर थ्री फेज सेट ऑफ वोल्टेजेस बना दिए। यहाँ पर एक बात याद रखने वाली है कि दिस smaller AC generator is connected in reverse manner to the bigger AC generator. That is, the rotor of the smaller AC generator is located at the stator of the bigger generator, and the stator of the smaller AC generator is located at the rotor of the bigger synchronous generator. तो ये इसमें है. तो खैर जब छोटे जनरेटर के वोल्टेजेस बने तो उसको थ्री फेज रेक्टिफायर से गुजार कर बड़े जनरेटर को डीसी फील्ड करंट मिल गया, और जब बड़े जनरेटर को डीसी फील्ड करंट मिला तो इसने इस जगह पर अपनी फाइनल आउटपुट यानी थ्री फेज सेट ऑफ वोल्टेजेस बना दी. तो इसमें कोई सवाल तो नहीं है, हम आगे जाएं जी. तो नेक्स्ट है जनाब पायलट एक्साइटर. The only disadvantage that we faced in the brushless exciter was that we need a separate three-phase low current supply for the provision of DC field current to the smaller AC generator. So the system was not fully independent, although it avoided the use of slip rings and carbon brushes that was needed in bigger AC generators, but still the system was not fully independent. So to introduce a fully independent system, what happened that machine designers mounted permanent magnets on the rotor of the bigger generator. Now these permanent magnets produced a fixed magnetic field in the rotor winding. Now we all know that whenever a synchronous generator works, we provide mechanical energy to the rotor. So when the mechanical energy is given to this rotor of the bigger synchronous generator, what happens that the fixed magnetic field at the rotor winding becomes the rotational magnetic field. And now due to this rotational magnetic field of the rotor permanent magnets, the smaller AC generator gets three-phase set of voltages at its rotor winding. These three-phase set of voltages are converted to DC field current with the help of a three-phase rectifier here. So this is the exciter field, that is the field current of the smaller AC generator. Since the smaller AC generator is providing field to the bigger AC generator, so it is named as the exciter. Okay, so exciter field means smaller AC generators DC field current. So now this smaller AC generator has the DC field current and a mechanical energy. So what happens that it produces three-phase set of voltages at its output located at the rotor of the bigger AC generator. So this is the output of the exciter. Exciter armature means the stator of exciter, where it produces three-phase set of voltages. We all know that a synchronous generator produces three-phase set of voltages as its output at the stator of the machine. So this is the stator of the smaller generator, which is producing three-phase set of voltages. So these three-phase set of voltages are rectified using this three-phase rectifier, and hence the bigger AC generator gets a DC field current in its field winding. Now using this DC field current and the mechanical energy provided at the shaft of the bigger synchronous generator, the bigger synchronous generator produces electricity, that is three-phase set of voltages at its output. Now this scheme is entirely independent, or it is fully independent scheme. Why? We are not using any slip rings and carbon brushes, so we don't have to replace the slip rings and carbon brushes periodically. And in addition to this facility, we don't even have to provide either the generator with a DC power supply or the generator with a small AC power supply. Rather, the field current of the smaller AC generator is provided by means of magnetic induction between the uh, field winding of the smaller AC generator and the rotational magnetic field of the rotor of the bigger synchronous generator. So this scheme is the best scheme available for the provision of DC field current, but therefore it is the most expensive scheme that is available. Why? Because these permanent magnets are quite costly. So although this scheme is fully independent and it has a lot of advantages, but it is expensive. So we use these schemes uh, for bigger synchronous generators mounted on hydroelectric dams or the places where electricity is being continuously produced without any gaps, and at those places obviously this scheme is viable economically. Otherwise, in our local generators that we use in our homes or domestic uses, this scheme is quite expensive. So this was the first half of the lecture we wanted to complete. तो अगर आपका कोई सवाल है तो आप पूछ सकते हैं जी। समझ आ गया आपको? चैनल जबरदस्त हो गया। अच्छा, एक छोटी सी बात इसमें है, द स्पीड ऑफ रोटेशन ऑफ अ सिंक्रोनस जनरेटर। तो द स्पीड ऑफ रोटेशन ऑफ सिंक्रोनस जनरेटर, देखें चैप्टर 4 में हम लोगों ने एक इक्वेशन पढ़ी थी कि nm इक्वल्स टू 120 f अपॉन p, और हमने कहा था कि ये जो इक्वेशन है ये एक स्पीड ऑफ एसी मशीन को, मैकेनिकल स्पीड ऑफ एसी मशीन को रिप्रेजेंट कर रही है। तो ये जो इक्वेशन 4.34 है ये बिल्कुल वही चैप्टर 4 की ही इक्वेशन है। तो अगर आपने एक जनरेटर की मैकेनिकल स्पीड मालूम करनी हो, एक एसी मशीन की मैकेनिकल स्पीड मालूम करनी हो, तो बहुत आसान सी बात है कि इसको अगर हम रीअरेंज कर लें इस इक्वेशन को, तो ये ऐसे लिखी जा सकती है nm इक्वल्स टू 120 f अपॉन p। तो आपको पता है कि पाकिस्तान के नेशनल ग्रिड में जो फ्रीक्वेंसी है वो 50 हर्ट्ज है। तो अगर एक ऐसी मशीन है कि जो 50 हर्ट्ज पे ऑपरेट कर रही है और उसके नंबर ऑफ पोल्स 4 हैं, तो उसकी जो मैकेनिकल स्पीड ऑफ रोटेशन मालूम की जाएगी, वो मैकेनिकल स्पीड ऑफ रोटेशन 120 मल्टीप्लाई बाय 50 डिवाइडेड बाय 4 से होगी। तो अगर आप इसको करते हैं कैलकुलेटर पर, ज़रा मैं कैलकुलेटर खोल लूँ जी। तो 120 मल्टीप्लाई बाय 50 किया 6000 हो गया, डिवाइडेड बाय 4 किया तो 1500 आ गया। तो पता है चला कि अगर एक मशीन है जो पाकिस्तानी सिस्टम पर काम कर रही है 50 हर्ट्ज पर और उसके 4 पोल्स हैं, तो उसकी जो मैकेनिकल स्पीड ऑफ रोटेशन है वो 1500 आरपीएम होगी। तो इस आर्टिकल 5.2 में बस यही बताया हुआ था कि किस तरह से एक सिंक्रोनस जनरेटर की जो है वो स्पीड जो है वो कैलकुलेट की जा सकती है। तो इंशाल्लाह अब 10:30 जो है वो हम सेकेंड हाफ ऑफ द लेक्चर स्टार्ट करेंगे, जहां पर हम इंटरनली जनरेटेड वोल्टेज जो है उसको डिस्कस करेंगे। अभी तक जो आपने पढ़ा है इस पे कोई सवाल करना चाहे तो कर सकते हैं जी। तो आपने सेकेंड हाफ जो है वो आपने दूसरे वाला लेक्चर का लिंक ज्वाइन कर लेना है, ठीक है जी। और उसमें हम इंशाल्लाह जो है वो सेकेंड हाफ मुकम्मल करके तो आपको इंशाल्लाह फ्री कर देंगे, ठीक है। थैंक यू।
ओके सर।
हाफिज़।